God. Okay, so as we were saying, let's assume that we have, yeah, you have a couple of meetings to attend, right? So let's just call them meetings. And every meeting, right, can be described with two things: their starting time and their end time. Let's call the starting time S and the ending time E, right? And you want to, so your goal is to simply maximize the number of meetings to attend. So you want to maximize the number of, that's the crucial thing, the number of meetings to attend. So let's assume we have a meeting that starts at 2 a.m. to, let's say, 10 a.m. Let's say you have a meeting that starts at, let's say, 3 a.m. to, let's say, 7 a.m. Let's assume you have a meeting that starts at, 7 a.m. to, let's say, 1 p.m. Just like, just cool stuff like that, right? Then you want to maximize the number of meetings you want to attend. Note, you can't attend 2 meetings at the same time, right? So you want you to, just find the greatest number of meetings you can attend. That's a maximization problem, right? This is a very typical intervals problem. So when you get something like this, or, you represent the data points as intervals, like a starting time and an ending time. One of the most, helpful ways to approach it is to kind of, visualize it on a number line, right? So you can draw a long number line here, and then we can just calibrate it very quickly. This is 1, you have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So perfect. Okay, so then we have 2, right? We have 2 here to 10. 13, 12, 11, 10. All right, we have this here. Let's just put this here very quickly. And then we have 3 to 7, 3, 10, 9, 8, 7, 3, 12, 5, 6. It's 6, don't worry. We used to manage with it. Let's just do some sketch, honestly. It doesn't matter. Okay. You just have this here. Then we have 1 to 5 here. So this is a problem you have, right? And now you want to maximize the number of meetings you can attend. So we went over a kind of logic last week, but I just want somebody to just give me an idea how you think, let's label this A, B, C, and D. A, B, C, and D. So looking at this, what meetings do you think we should attend? What meetings do you think we should attend? Anyone? What meetings do you think? Let's label this 1, 2, 3, 4. Let's first look at this. Let's first look at this part, the intervals part here. What meetings do you think would be good to attend? Note, all the meetings have the same value. They are not weighted. They have the same value. So what meetings do you think would be plausible to attend? Anyone? Or what combination do you think is best to maximize the number of meetings to attend? Anyone?
1 and 3, I guess.
1 and 3, right? Okay, so now let's use the intervals grid. Let's use
I said 4 and 3.
4 and 3, right? Okay, let's use the grid here. I think that'll make it clearer to people. So is it A and B, A and D, A and C, or whatsoever? So those of you just joined, we're just trying to maximize, our goal is to maximize the number of meetings we can attend, but there's a restriction. Our restriction is that you cannot be in more than one meeting at a time. Cannot be in more than one meeting in more than one at a time, right? So here, looking at this grid, what meetings do you think would be good to attend? What picks do you think helps? What combination are you thinking of?
C and D.
B and D?
C and D.
C and D. Okay, there's C here and there's D here. That's true. That's a good pick. Is that the only one? Is that the only one? Is that the only one?
B and C.
B and
also
C.
do B and C.
Right. But that's also 2, right? That's also team meetings. So either B and C, either works, right? Either is perfect. I hope you all agree with that. You agree with that? They both give you 2 meetings to attend. Sounds good?
Yeah.
Okay.
So I have a question though.
Yeah, well, go for it.
So what if it was 2,7 instead of 3,7 instead of
3,7. 1, 2, so
3,7 instead of 3,6.
So like you mean 3 to this? You mean like this?
Yeah. You see,
ask the question. So this is 3, right?
Yeah.
4, 5, 6, 7, and this is 7, right?
Yeah.
So you mean like this?
Yeah. So because like it's the one that I just drew and see like the ending and the like beginning part.
Oh, I get what you're trying to say. When they start here, right? These are not overlapping, right? That means we will say this ends and then this begins. That is a very good question to ask in an interview, right? So you can ask, if a meeting ends at, let's say, 7, another meeting starts at 7, right? Can you attend both? And the answer is yes, right? You can attend both. Does that make sense? And that is a very good thing to clarify in an interview, right? Do you understand the question he asked? Do you understand?
Yeah, but I'm confused why he said yes, because at 7 the meeting has already started.
Exactly.
So
Right. It's a constraint to the problem, right? So that's why you clarify. You ask the interviewer that. And per our question, I'm saying yes, it's possible. You can attend both, right? The reason being this, they don't necessarily overlap. It's more like this ends with this. Now, the interviewer may say you can't. It all depends on what they give you, right? So that's point you have to, and to be honest, handling these two cases is not anything difficult, as you will see, right? So if you come across this question, ask the interviewer for them to clarify. We are saying, yes, you can attend both of them, right? If they say you can't attend, so don't make the assumption, right? You can always ask to clarify. Does that make sense?
yeah.
Okay, good stuff. So now let's see how, so now let's have this question. Now let's actually add E as we have here like this. What is the best combination of meetings to choose now? We've added E. What's the best combination of meetings? Is it the same as we had before?
I think the one before it's also it's also
Exactly.
possible.
It still work, right? And you can also do E and C, right?
And
It still work.
also do yes.
Yeah, exactly. So then we said, now the question becomes, then how did we choose? Let's take one answer. We said D and C. How did we choose D and C? How did we choose D and C? So it's actually what we're doing right now is what we call greedy algorithms. But I want us to focus on something called the greedy rule. So now, how did we choose D and C? Anyone? How did we choose D and C? Or E and C, or B and C, whichever answer you choose? How did we choose them?
Okay, so we chose D and C because by the time D ends, C had not yet started, so we can rush to C before it starts.
Right, that's true, right? Now, it's the same thing for E and C, right? After E ends, then we choose this. After this ends, we choose this, right? Now, this, as you can see, this has been organized in some order. By drawing this number line out here, we have enforced some order on it. What is that order? We have arranged these intervals based on their starting times. Can you see it? Here, we see D starting, D being first here because we have brought it forward. We gave the start time of 1, right? 1, 5. The same thing for the starting time of 3, the starting time of this. But when you get a question like this in an interview, there's no guarantee that it's going to be in a sorted order. So this translation you have made from here to here is actually through a sorting order. Does that make sense? Does that make sense?
Yeah.
Some of these intervals questions, that's the first thing you want to observe. As you translate them to a number line representation like so, you should understand that you've actually, sorted them in some order. That is number 1. Number 2 becomes, what sort order did you impose on it? Did you sort based on the start time or did you sort based on the end time? Anyone? Here, based on this one, did we sort based on start time or we sorted based on end time?
Well, I think based on end time.
Okay, so let's note that here. So sort order. So someone say we sorted based on the end time. Now, is that ascending or descending? Is that ascending or descending? Do you sort in ascending or descending?
Oh, it's ascending.
Ascending. Okay. Anybody has a different answer?
I think it's based on the start time.
Okay, someone else said based on the start time. I want to show you how this thing can be a bit tricky. That's why I've chosen this a bit complicated one. Okay, someone also said it's start time. Is that ascending or descending?
It's ascending.
Okay, someone also says ascended. Good. Now, one is right, one is not right. The one that is not right is it just has a slight twist. Now, the reason why we're giving this thing is because of the example you see before you. And look at the example you see before you. This guy ends first, right? So then it comes first. Then these two guys end next. And then they kind of like, this guy and this guy ends next. So but it's like the same. So this guy comes next. Then this guy comes next, right? Then this guy ends next. And this thing comes next. So it's easy to assume, it's easy to conclude that they are actually, sorted according to ascending order in end time. Can we all see it? It's very easy to conclude that based on the example you have here. That's why in an interview, when you're given a question, they give like 2 or 3 examples. I mean, in a good interview, what you do is that you try to, kind of apply this visualization to every one of those examples. You don't just take one example and then jump into your solution because that can actually end up tricking you. Now, Here, it's actually being sorted according to start time in ascending order. So as you can see, the start time of 1 comes first, then start time of 3, there's start time of 4, start time of 7, and so on and so forth. So this has actually been sorted in ascending order of start time. Not just that, it has also been sorted in descending order of end time. If you look carefully, this guy ends last, so we can see it here, right? So now this has a bigger number. Descending order means the bigger comes first, right? So if I read from here, right? If you read from here, this guy comes first, right? This guy comes next. Then this guy comes next. Then this guy comes next. Does that make sense? Do you get the two things? So it's been sorted both in descending order of end time and ascending order of start time. But kind of like, there's ascending order of start time is relatively simpler, right? Like as we discussed last week, if you have a collection like this, let's call it times, and you just do times.sort, it's going to sort it based on the first number, right? It's just going to sort it based on the first number. And then we know that our first number is our start time. Does that make sense to everyone?
Yeah.
Okay, good. So let's stick with that. So we know number 1 is we sort. So number 1 thing for most interval problems is to sort. So we sort based on start times. Okay. Then number 2 is, now let's consider what we call an overlap. So we wanted to maximize the number of meetings to attend. That means that when you come across some conflict like this, you have to make a decision as whether I should attend you or not, right? Now, that's what I should attend. That's, thing you see as well called the overlap. So now let's come to the decision. D and E are overlapping here, right? Which one should we choose to attend? That is the most crucial thing about the greedy algorithm, what we call the greedy rule, right? The greedy rule, that is what you're going to make the decision in case you come across some problem. So here, we've come across Z and E that are overlapping, and we want to maximize the number of meetings to attend. Don't forget our goal. What do we do here? Which one do we choose? Do we choose both? We can't choose both because of our restriction. Do we choose none? If you choose none, you're not maximizing the number of intervals. That means you have to choose something, right? You have to choose one. But which one do you choose between D and E? Anyone?
D.
Which one?
D.
D. Okay, somebody says we choose D. Anybody have something else? Someone says we choose D. Anybody else?
Okay, I think since we are trying to attend as many meetings as possible, we are supposed to choose E because it's a shorter meeting. That means it leaves more time for other meetings.
Okay, someone also says we choose E. Okay, anybody have
presuming there are other meetings before E.
Okay, so let's restrict ourselves to this. This is what we have, right? So let's restrict ourselves to this setup. That's what is before E is potentially only there's actually even more overlap here. But let's focus on just D and E, just D and E. Let's assume in your world you just have D and E, right? So let's assume this is our world. Let me draw a sketch here. I don't know, it's getting a bit messy. See, let's remove this. But okay, so someone says D, someone says E. Let them justify. The D person, why will he choose D? Why will he choose D? The one who said D. Or anybody else who wants to justify that. Why do you think D would be a good pick?
Okay, so
sorry.
Go for it.
Yeah, we want to maximize the number of meetings we have. So it's easier if we end earlier so we can start other meetings.
Right. That is literally the rationale, right? And that is what we call the greedy rule. Right. So once you get this enlightenment, once you've identified this thing, you are almost done, right, with your whole solution. Because if I come across 2 meetings, right, that have a conflict, what is it? Let's choose yellow. If I come across 2 meetings that have a conflict, the rationale is this: hey, I want to end early and then I can start the next one. Because if you choose the one that ends late, you're going to be in trouble, right? Does that make sense? So that's the whole thing. I want to end as early as possible so I get more time to do the others. Does that make sense?
No, please, can you take that again?
Okay, so let's look at this. So let's assume you have a machine that is working, that is making blocks, right? That is making blocks like this. Machine that is making blocks. I'm trying to use different problems to kind of enlighten you so that you can think about. So when you get a question and some intervals and something else, you can still think about that. But it's these greedy algorithms. Let's assume you have a machine that makes blocks, right? And then there's this machine, and then there's a couple, there's a bunch of blocks to make, right? Then there's this block that takes, let's say, 50 milliseconds, right? Then there's this block that takes 30 milliseconds to make. There's this block that takes 10 milliseconds to make. And now, and there's just one machine you have. It's just this machine you have that can make all these blocks, right? Now, all the blocks, when you sell them, you get the same amount of money. In other words, their weight is the same. It's the same as the meetings here. It doesn't matter how long you take, the benefits I get from the meeting is the same. That benefit is what we call weight. Okay, we're saying our weight is constant, right? So we just want to maximize the number of blocks, you can make, right? If this machine has only, let's say, 50 milliseconds to operate, if this machine has just 50 milliseconds to operate, right? We want to maximize it. So here, what is the best thing to do? The best thing to do is to simply make that block, right, that you can finish early and still have enough time to work on the rest. In other words, you want to finish making some block early, and then you get much more time out of this 50 millisecond to continue doing the next ones. That is basically what the problem is asking you to do. Does that make sense?
Yeah, thank you.
Good. So here, the rationale is this. You want to take that meeting that will allow you to end early, and then you have a lot of time. You have, a lot of remaining time to work on the other ones. Does that make sense? Because they have fixed meeting intervals. Now, you realize that if I do D first and I finish D, right, I'm here. If I do D and I'm done with D, I'm somewhere here, right? Like I'm here. Once I'm here, I still have C to explore. I still have C to explore. I still have maybe any other meetings to explore. Does that make sense? Does that make sense to everyone?
Yeah.
Okay,
Yes.
Let's even make D a bit trickier. Let's bring E here. Let's bring E here. Now, so I have here, if I choose this D, this one, I'm able to finish early. I'm able to do C. If I choose E and I do E, you realize that when I'm done with E, I can't do C because E and C have a conflict, right? So I can only do one meeting. Does that make sense? Does that make sense to everyone?
Yeah.
Okay, so that's the rationale here that, hey, if you come across a conflict, right, choose the guy that ends first. Choose the guy that ends first. Choose the guy that ends first. Somebody who wants to think reverse will also say, hey, start from here and choose the guy that ends last, right? But it's kind of like the same thing, right? It's just kind of a twisted analogy. Like if they choose here, you can be like, choose the guy that starts first. Like it's just, but I just wanted to think of one way across it. So let's go to a greedy rule. So one, you saw the start times, and number two, if there's an overlap, right? If there's an overlap, choose end first. Choose the interval that ends first. And we have explained why that ends first. We have explained why when you choose the one that ends first. It's simply because you want to have more time, to do the other ones. Another way to think about this is also this. The guy that ends first has a lower probability of colliding or of conflicting with other meetings. Does that make sense? The guy that ends first has less probability of conflicting with other ones that what do you call it? That come after it. This is what I mean. My English is becoming a problem. Look, if this guy ends first and this guy ends later, right? The probability that this guy conflicts with other meetings is very low. Do you agree? Do we?
Yeah.
Because if you take any other meetings here, right? If this guy conflicts with this meeting, if this guy here conflicts with this red one, it means this blue one also conflicts with it. If this guy conflicts with this one, it means this blue guy conflicts with it. This blue guy conflicts with this, but this guy does not conflict with it, right?
Yeah.
Doesn't make sense. Yeah, greedy algorithm. I feel like greedy is kind of like is the trickiest topic in some level. I mean, probably not as dynamic programming, but greedy is definitely like a very tricky concept too. Sometimes I think the greedy rule is like the most crucial part. And here, this is one way to identify it. And we've given the rationale, right? Okay, so that is number two. When there's an overlap, choose the interval that ends first. Then the next one I want you to consider is, what is the definition of an overlap? What is an overlap? If I have two intervals, 2, 10, and 3, 6. 2, 10, and 3, 6. How will I know if they overlap? So here we have sorted it, right? Number one was to sort. How do we know there's an overlap? Anyone, how do we know there's an overlap? This is the next crucial thing.
When the ending time of the first meeting is less than the how do you call it? The starting time of the it's greater than the starting time of the second meeting.
Like this, right?
Yeah.
Exactly. And that's an overlap. That is literally it, right? It's an overlap. Here we said when it's equal to, it's not an overlap, right? We said when it's equal to, you can still continue. So yeah, this is the definition of an overlap. If the ending time of this current one, right, is bigger than the start time of the second one, then there's an overlap. and you're done. You've basically solved this question. I'm supposed to write the code for this question, but do people understand this illustration? I'm gonna write some code, but I want you to understand this first. So as I write the code, it will make much more sense. Does everyone understand this?
Yeah.
Yeah.
Okay.
Cornelius,
Yeah.
must the start time of the first also be less than the start time of the second?
The start
'Cause-
time of the first be less than the start time of the second? Well,
Yeah.
not really. It can be equal to, right? But so for instance, this is what he's asking. We can have 2:10. They can actually be equal to, and then we can have 2:08, right? Is this an overlap? Is this an overlap? These two.
Yeah.
Why is it an overlap?
Okay, because the start time of
Exactly. This condition still checks out, right? This condition is still satisfied because
I
the ending time of this is bigger than this.
I was thinking that just using the first condition, what if like the second interval is on the left of the first interval?
Like this? Like 10, 10?
Let me see. Yeah, something like that.
Something like this is not an overlap, right? We are saying it's not an overlap because we are saying if the first meeting, right, ends at 10 and the second continues from 10 to 12, we are not treating it as an overlap. Does that make sense?
Yeah.
Yeah, we're not treating this as an overlap. But in the interview, you can clarify. The interview will be like, let's treat it as an overlap. So in that case, you just make this greater than or equal to, right?
Yeah.
Okay. Okay, let's go on to the code then. So let's just call our function maximize. Then we're going to have a couple of intervals here. Let's just call it meetings. Please, and always pay attention when I'm writing code, because sometimes I try to write the code in a different way so people can pick things up, right? Some programming stuff, you know. So now one thing we did was to sort, right? So let's sort our meetings. And we are sorting using .sort. That means going to sort it in place, right? And this is going to sort using the first item. So the intervals are in the form, the start time, start 1. We can even use a tuple, it doesn't matter, and 1. Then start 2 and 2, and so on and so forth, right? These are our intervals are. Okay, then we sort, and then the next thing we do is look at this. We're going to choose the first interval, right? We're going to call it, let's say, row. We're going to choose the first one, meetings index 0. We're assuming that there's at least one meeting, meetings index 0. So we choose the first one, and now we are coming to take that first one and then compare it to the others. So what I'm going to do, I'm going to be like for I in range, starting from the second meeting. So 1 to length of meetings, right? So let's take the current interval. So I'm going to take the second one. So I'm going to give it a start time. So let's say a start time. Let's call it start 2. And then an end time. And let's say it's S and E. I'm trying to make it very English, but you know, it is what it is. So let's call it S2 and E2. And that is equal to meetings. I've had this called destructuring, meetings of I. So, you know, an interval is of the form start time and end time, right? Start time and end time. If I assign it to a variable called S2 and E2, it will take the first one, put inside this variable, to take the second, put inside this variable. That's what I've done here for destructuring, right? Because meetings of I is a 2-item list or a 2-item tuple. It doesn't matter. So if I do this, it simply means put the first one inside this, put the second one inside this. That's what I've done here. Okay. So what I'm doing right now is this. I take the first, so as I've sorted out this, so I'll take D first. Then I'll try to compare D with the others. That is what row is. So row is going to start out as D. So you take D, you take the first, because the meeting has to start from somewhere. And I'm like, oh, let me try and start from the one that starts first. Let me assume that is the guy, right? So I'll take that first. Then I will go, all right, so I come here. So I take the meeting that is row, then I'm trying to compare it with the others. So starting from the second meeting in the sorted order. Does that make sense? Does this first part make sense? Does this make sense?
Yeah.
Are we sure it makes sense?
Yeah.
Okay, let's move on then. Then next, we're going to check for overlap, right? Then I'm checking if the first meeting I picked, if it overlaps with this second one. Note I is starting at 1, so this is going to be the second meeting, right? I'll be like, if overlap, right? How do I know if there's overlap? So you know that row is start 1 and 1, right? It's equal to row. In other words, the row I picked is just as a start. Row is also, it's also a tuple, right? Something like 1, 2. This is how row looks like, right? So here I'm just distracting it into start 1 and end 1. Does that make sense to everyone?
Yeah.
Okay. If people don't want me to destructure it, I can just go ahead and just write. Overlap condition was if row index 1, that is, if the end time of row, right, if it's bigger than the start time of S2 of this one, right, then that means there's an overlap, right? So we know there's an overlap. Now, if there's an overlap, what do we do? Is a condition. If there's an overlap, what did we do? Which of them did we take? We had D and E. And we know there's an overlap. Which one do we maintain? Which one do we throw away?
Cornelius.
Yeah. Samuel, what's the question?
Oh, is that I or L? The range.
This is I. This is 1.
Okay.
And this is I. Yeah, and this is I. Good. So D and E. So here row is D because that has a higher start time. So that's what we picked here. And E is the one we have here, right? So we said there's an overlap here. That's what this condition means. So if there's an overlap, we have to throw away one and we have to maintain the other. Which one do we throw away between D and E?
So we throw away E and pick D because it's
exactly. Exactly, right? We throw away E and we pick D. So row, we're going to now reset row to be like, our meeting can't really start with D, so we now have to change row to E, right? So here is the same as doing this. It's the same as doing row index 1, that is the end time of row should now be, look at this, the end time of row should now be the minimum. So this row, the minimum of row index 1 and E2. Can somebody just look at this and tell me? So the question we discussed was which of the meetings should you do? But now I'm solving a question of, it's the same thing. But I mean, if I want to just I can just have a result variable here and just append, right? But now what I'm trying to solve here right now is how many meetings can we do? Or how many meetings should we remove? It's the same thing reverse thinking. But even before you think about that, I want you to look at this condition and see what we've done here. What do you think we've done here? This thing we have done here. What do you think we have done here? So we said if there's an overlap, right, then the ending time of row should be equal to the minimum of this and this. So here, what is row? Is row what we have removed or what we have kept?
We are choosing the minimum between the two end times. So the one with the earliest end time is what we are choosing. So
exactly. So we are choosing this. D. Exactly. Does that make sense to everyone?
Yeah.
Yeah.
Okay, good. And now, else, if there's no overlap, what does that mean? That means that whatever row is, that meeting, that thing can be done. Whatever row is, we can just empty it in, right? Whatever row is, we can just store it. Does that make sense? So this else block is if there's no overlap, right? If there's no overlap, right? So let's assume the question we're solving is we want to count the number of meetings we can do, right? We want to count the number of meetings we can do. Okay. So here we can do count plus equals 1. And then we reset row to be, so now what does row become? Row becomes the new interval. We now start at the new interval. There's left one last thing, but Eden, question.
Yeah, I wanted to ask that in our if block where we are assigning the row 1 to be equal to the minimum of row 1 and E2, since we're assuming that, are we still assuming that the intervals are tuples? Because I was asking if it would be possible to to change the elements inside the tuple.
Oh, this one. So we're actually treating them as lists, as I have here. As lists here. Yeah, tuples are immutable, right? Tuples are immutable. Yeah, I'm treating it as a list here. Did you get what you're trying to say? He's asking if we're treating this as tuples. But if you have tuples, you can do row index 1 is equal to, right? Tuples are immutable. You can't change the elements inside them. Does that make sense?
Yeah.
Yeah. Okay. So here we get to a condition, right? If there's an overlap, we are like, hey, let's reset it, right? Let's reset this. we just reset this guy here. That's what we're doing here. If there's an overlap, right? And then if there's no overlap, we are like count plus equals 1. That means like, hey, we can do one meeting. So what that looks like is this. So that's like if we have D like this, and then you have E here like this, right? So here, row came in as this. Then you check there's no overlap. So then it goes to this condition, right? Then you increase your count, how many meetings you can do by 1. Then you reset row to now be E, right? Then so row jumps from here to now here to see if it can also compute other overlaps and stuff. Does that make sense?
Yeah.
Okay. There's one last condition. If you take this, even this scenario I gave here, when this for loop ends, what will be the value of count? What will be the value of count when this for loop ends? Anyone? When this for loop ends, what will be the value for count?
1.
It will be 1. But is that the right answer?
No.
Is that the right answer? I want to show you another thing in solving programming questions.
No.
What
No.
should be the answer?
2.
It should be 2,
2.
right? Okay, so that means at the end, you have to add 1 to count. This is the reason. Now, almost always, whenever you are accumulating your result inside some condition, like you're doing here, right? Like you what do you call it? Let me use this colored one. He realized that you actually update your result in some condition here, and then you reset your accumulator to an element. Almost always, when the for loop ends, something is going to be stuck in, right? It's going to be stuck in. Realize here, when I'm done with the for loop, row will be stuck on the E, as you can see here, which is also an interval. So then you increment it here. It's a very common thing in programming, as you would see. Like it's a very common. Some people finish and there's one element missing, or there's some interval missing, or there's some item missing. That is because they're accumulating inside either an F block or an else block or an elif block, and they're resetting the accumulator. But when the for loop ends, it just doesn't, they don't account for that ending part. Does that make sense?
Yeah.
Does that make sense to everyone? That is +1 is because like BBA Kemuaha, right? You reset row to E now, but then the for loop has ended, right? So then we have to do the +1 to account for this interval E that we reset here. Does that make sense? Yeah.
So I wanted to ask, if we initially initialize our counter as 1, would there be a problem? Because I feel like
that's going to be a problem, right?
Yeah, because you are jumping rows.
Yes. So if you initialize a counter to say 1, right? If you are guaranteed that the list is always going to be a non-empty list, right? Then that is going to work. Where you don't have to do the plus 1 here, right? But if you don't have that guarantee, then it becomes a tricky thing. That means you may return 1 when the list is empty, but instead of the 0, right? Does that make sense? Yeah. There's also the other condition. The other condition can also be this. Sometimes, see here, we're accumulating how many meetings we can do. If once you accumulate how many meetings you removed, then if you just reset it to count is equal to 1 here, and then you omit this, you may also end up being in a situation. Can we see the situation? If you end up being the removal, you have to cancel. So if you want to, so this is how many meetings we ended up keeping, right? If you want to do the removal, then what do? We take this guy and bring this guy here, right? That is, whenever there's an overlap, right? This guy is like, whenever there's an overlap, you discard, let's say, the maximum of this one, right? So you increase this one by 1, right? Okay, you can still manipulate that to easily work. So it's the same template, we're just moving it around and so on and so forth. The other question can also be, I want you to give me the meetings that were really done. That one to be simple, right? You just do some appending here, right? Then at the end, you just append the last meeting here. Does that make sense? Yeah, so that is when it becomes an issue if you just initialize your count to some value here, right? Instead of appending it to the last one here. Does that make sense?
Yeah.
Yeah. Well, Eden, does that make sense? Why it's not the best to just initialize? Why it's not the perfect case to always initialize your accumulator, like the result here? Because if you want to really accumulate the meetings you ended up doing, then you only know that value when you reset it here, right? You may only know that when you reset it here. Therefore, you have to append the last one here. Does that make sense?
Yeah, it does. Thank you.
Yeah. Anybody has any questions? Yeah, go for it.
So in case we were to append to a list, right?
Yeah.
And we keep changing the first index of our row. So like, how do we
exactly? So for that, you have to change more than the first one, right? So for that, So if in case you really want to accumulate the actual meetings that you end up doing, here you have to actually use a check, right? So you have to, instead of just the last element, you also have to update, you may also have to update the first element, right? The first element. Does that make sense? Because if it's something like this, if you have this as D and E, which one will you end up keeping? Which one will you remove?
I'll keep E and
you keep E, right? But you see, when row first comes in, the starting point of row is going to be that of D, right? But they're making the decision based on the end point. So for that, you also have to update the starting. Does that make sense?
Okay.
Yeah. So if you want to do that, then you have to just do it. It can simply be like if E2 is less than row of 1, then row is equal to S2 E2, right?
Oh.
Like this. Does that make sense?
Yeah, that makes sense.
Okay. Anybody has any question? Okay. So this is, so we just did one thing and we visited to solve like 4 different questions, right? Which meetings to keep, which meetings to remove, how many meetings do I keep, how many meetings do I remove, and so on and so forth. We've done the definition of an overlap and all these things. So I just wanted to take some time. This week, God willing, go over the intervals questions, do some practice. You realize that, let me show you. Most of the intervals questions that actually come across are just, just manipulations of what we just did. There's another meeting called meeting rooms. There's a consistent question called meeting rooms. You should definitely make time to go through. Let me see. Screens. So one. Can you see my screen?
Yeah.
People are watching me watch Fluffy. All right. It's a very funny guy. Okay. Yeah. Let's go to intervals. Yeah. I tried to pull up a couple. Okay. I wanted us to do backtracking today. You're beaten by time too. No, I know what I'll do. I'll just give you people some secrets on backtracking. It's not necessarily to about something very quick and to make sense. Okay. So what we just did was, which one did we even do? I mean, we can do. I don't. Okay, let's look at not overlapping intervals. Okay. So this has given an array of intervals, right? Return the minimum number of intervals you need to remove to make them. So they say minimum to remove. The same as you want to maximize how many you keep, right? It's kind of like just a question we solve, but just reworded differently. Let's look at my solutions. July 23rd, 2023. Let's look at this. Let's look at this. Okay, good. We sorted. Our result is 0. We make rows. So even here, I'll just keep in the end value, right? The end one. If there's an overlap, choose a minimum, increase your results. If there's no one, then just go here, right? This just like as we did. Let's look at the next question. Let's go to insert interval. Insert interval to see. Oh, I said they almost always have the same one. You see, I've been practicing and revising. Very crucial. You're not a robot, you forget things. So you have to retry, you practice, on and on and on. So you're here you want to insert interval. Why was there no sorting here? I've already sorted for you. Oh yeah, it's already been sorted for you, right? But don't make that assumption. If it's sorted for you, if it's not sorted, I think almost every interval for you end up sorting, right? Because when once you sort, as you saw, it becomes like you put it on a number line, right? It becomes very easy to manipulate, right? So this is like if there's an overlap, blah, blah, blah. If there's no overlap, put this in and there. So here you realize that here at the end, there's something that is stuck in also. Then they just add it and try. This one is meeting is also, it's locked. There's another website, it's probably been taken down. It's called, give me a second. It's called Lens Code. Some Chinese website, it's probably been taken down. I don't like to use it, but if you don't want to pay for a premium, meeting room is a pretty common question actually. Let's see. Let's see. Yeah, if you're very ambitious, you can just look at it. Okay, this person has links, good link to it. Right, I don't have time for this. Please don't give your information to these websites. So given a number of meetings, consider start time and end time. You want to determine if you can attend all meetings, right? If you can attend all meetings, that's like you're checking for overlaps, right? and so on and so forth. Or here they actually even use the input as tuples. Okay, so that is after that. So please go on this week, do all the intervals questions. If you do the ones on the NEET code 150 first. If you're done in time, go to the NEET code all and just do the easy and mediums. You don't need to bother with the hards yet. Okay, let me brush you through backtracking. Intervals took a bit more time than I thought it would. So let's take a quick look at that. I want to show you something very simple. Like you love it, trust me. Backtracking, it used to be one of those things I was so scared of. I remember sometime when I started recruiting, I started practicing and doing all these things. Other topics, people used to say they're so scary and everything. So at some point, I'll ask somebody, like, hey, do you understand this screen? They'll be like, no, even men understand it, right? But you learn it yourself, realize it's not scary as people make it seem. One of it is backtracking. Let me show you. It's not the worst, right? If you didn't understand intervals, don't worry. Put it behind and let's move on, right? Let's move on. Just follow me carefully for backtracking. You get something. We are beaten by time, so I just rush through just a few things. I'm going to explain backtracking. As I said, some people have already done backtracking before. We basically implement it like recursively. Recursion. If you're following a recursion, please go and revise it. We said our secret source for recursion is assume the function works, correct? Then you just call it on the subproblems. If you haven't done recursion, please go and watch our video. It's so good. I don't know. Yeah. So let's go through backtracking. Now look at this problem you want to do. I'm going to use this problem. Let's assume, right? You have this problem called combination sum. Yeah, that's the question I used to learn backtracking, combination sum. Assume you have a list of numbers. Well, let's make it long. And you want to know, you do the easier one. I want to know if you can add any subset of your numbers to get target. So now let's define our target. Our target is going to be the number 8. So we have a list of numbers, right? I want to see if we can add, any, it can be 1, it can be 3, it can be, if we can add any combination of these to get our target. That is 8 here. Does the question make sense to anyone? I want to see if we can add any of these things to get our target 8 here. Does it make sense to everyone? That's a problem. Does the problem make sense? Understand the problem, you understand the solution. Does the problem make sense to everyone? Only one person? Does you understand this problem? Nobody? Yeah. Good.
We do.
Now,
we do.
Good. Now, you see, when you see a problem like this, you're thinking for loop, but you're like, for loop, I'll take 2. You're like, I'll take 2 and try to add 2 to 3 and 5 and 4 and 1. Then I'll be like, but that is a bit. I mean, if you look at it right now, it's like 3 plus 5 will give you 8, right? Like 3 plus 1 plus 4 will give you 8. But you're thinking that you're like, there's so many for loops and messes and everything. That is when backtracking comes in. Backtracking comes in when everything seems so messy and so messed up. Backtracking comes in, number 1. Number 2, if you want to find a combination of something, of your input to achieve some target, think backtracking. Why do I say this? Let me show you the secret sauce about backtracking. Now, the secret sauce to solve this question is this. We take our list like this, 2, 3, 5, 1. Then you start on the first number here. Then you make a decision. Should I include or should I exclude? This is a decision you make every time in backtracking problems. Should I include or should I exclude? When I include you, so let's say this is your accumulated. This is what you are thinking will probably work, right? So if I include you, I add you to my accumulated set. If I exclude you, I don't add you, so my set is empty. Does that make sense? What the accumulated means. If I choose to include you, I add you to my accumulated set. If I choose to exclude you, I don't add you. Does that make sense? That is the next thing. Yeah. So now we want to find a combination, of this that will add up to 8. So what we're going to do is this. The next thing I want to also tell you is that there's no repetition. I don't want you to bother with repetition here. It's no repetition. That means that you can use a number just once, right? Like if you choose the 2 here, you can only use it once in your accumulation, right? So this is how we're going to solve it. So then we start on the first number 2. Should I include or exclude? Now look at this. You're a human being. You can look at the question and be like, don't include 2 or include 2, like, because you can see it. But when writing code, the computer doesn't know yet. It doesn't know the numbers here. So there are only 2 decisions to make. Well, let me include 2, and let me also exclude 2. I don't know which one leads to my solution. So I'm going to make, the decision to both include and to exclude, right? So we draw a branch here. Let's include 2 here to my accumulated set, and let's exclude 2. So we're done with 2. Then we move here. Does that make sense to everyone? Does this make sense? I can choose or exclude. I don't know which one will lead me to the solution, so let me do both, right? Let me come to 3. Do I include 3 or exclude 3? Now, here on this branch, you can see why it's recursion now. You make the recursive call here, make the recursive call here too, right? So now you're on the 2, you're like, should I include 3 or exclude 3? You're like, I don't know either to give me the answer, so let's include it. I get 2, 3, like, let's exclude 3. Then you get, if you exclude 3 here, you have only 2. Here, so you come to this branch too. Should I include 3? You're like, yep, include 3. Should I exclude 3? Yep, exclude 3. So you have something like this. Then we come to the next one. We're on 5. Should I include 5? You're like, yep, include 5, 2, 3, 5. Should I exclude 5? Yep, exclude. You get 2, 3. You still get your 2, 3 here. And here, should I include 5? Yes, include 5. Should I exclude 5? Yep, exclude 5. We have the 2 here. Should I include 5? Yes, include 5. Should I exclude 5? Yes, exclude 5. Like this. Should I include 5? You get 5 here. Should I exclude 5? You used to get the empty list here. Does that make sense? Does it make sense to everyone? That's what we've done make sense to everyone? Hello? Did Rapture listen on this call? No, else I wouldn't be here.
Yeah.
Okay, so this is what we have so far. And so you see how we built it. I just want to see how I built this tree, right? At each point, I made a decision. Should I include or exclude, right? Now, we could have just gone down one branch, but I just did it, kind of level-wise for you to see something. I thought I'll show you why it's good to go just one level like that. And that is what we call memoization comes in. And then you switch to dynamic programming. You're not even there yet. This is just enough. I told you, master backtracking will be so fine. So now, as you can see, as you build this your accumulated set here, does any combination give you the target you want? 8? Does any combination give you the target?
Yeah.
Good, you can see it here. So if somebody looks very carefully, now let's assume our list is just ending up to here. If you look carefully and you look down here, you realize that we have built all possible subsets of our input list 2, 3, 5. If you look carefully, can everybody see it? What are the subsets of 2, 3, 5? We know there'll be 8, right? Because they taught this in high school. The number subset is called the 2 to the power n, where n is the number of numbers. Somebody's missing the high school teacher. Yep, that was useful. So what are the subsets? The empty list is a subset of every set, right? There's 5 here, there's 3, there's 2, there's 2, 3, there's 2, 5, there's 3, 5, and there's 2, 3, 5. So here, that's what you were thinking. You're like, I have to find some combination, blah, 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 blah. And this is literally what you have generated down here. So to generate this combination, this is the code: include, exclude, and move the pointer forward. And as you include, exclude, as you form your intermediate set, you then just compute the sum and be like, hey, are you equal to target? If it's equal to target, you can just stop and return true. If it's not equal to target, you then continue your recursive approach, and that is all. That's literally the solution. I'm going to write the code briefly because we're beating by time. Next week, we delve much deeper into it. So if I want to solve this question, this is how I'll do it. Def, let's say find sum. Here, I'm even going to find the sum for you. No, let's not find sum. Let's just be like, can do. And we're going to have, you're going to have a list of numbers, right? Like this. Look what I'm going to do here. I'm going to write an inner function here. So today and next, we're going to use this inner function a lot. Let's call it solve. And what solve is going to do is this. Please follow me carefully. Solve is going to take an index, I, and a stack. My stack is going to be the accumulator you are seeing here. The stack is going to be the accumulator. That is going to be the accumulator. That's the stack. This index I is going to be that arrows you have here, that number, what it's standing on. Does that make sense? That's what I and stack are make sense to everyone. Does that make sense?
Yeah.
Okay, good stuff. Then the first thing I'll do, for now, I'm going to leave the edge cases out. I'll just be like, if the sum of my stack, this function also takes target. It also takes target, don't forget. We want to see, if the sum of the stack is equal to target, that means I can do it, right? So tada, check mark, right? Does that make sense to everyone?
Yeah.
Then we return. If that is not the case, right, then what I'm going to do is I'm going to, okay, let me make a decision. Do I include the number here or not, right? So I'm going to be like, include is going to be solve. Oh, no, sorry. Include, we have to perform the include step. So let's use a comment here. Include. What is include means you append it to the stack, right? So stack dot append the current number. So nums index I. All right. And then when you include, what do? You call your function again, solve. Now you go on to the next number because you don't want to. So now that's like, if you included it, now move on to the next one. Move on to the next one, right? So you call solve on I plus 1 because you said I is the number you're currently standing on the stack. That's it. To exclude, how do I exclude? To exclude, realize that here I've appended it to the stack. That's the including here. I want to exclude, I want to remove it from my stack. That is literally it. So exclude is you do stack.pop. That's when you remove it. Then you call solve again, move on to the next number, and then you're stuck. That is literally the whole code. That is the whole solution. Trust me. The only thing left is your base case. Now you want to make sure that I is not out of bounds, right? So you realize that you're going I plus 1, I plus 1. You want to make sure that your I doesn't go out of bounds, right? So just that check here, right? Does that make sense? Just put that check here. Now, if you've never returned here and I goes out of bounds, that means it's never possible, right? It's never possible for you to make the sum. So you can be like, if I, it's equal to the length of stack, that means it's gone out of bounds, you can just return false. Or for now, I'm just going to say return false. Well, next year, I'll show you how to use a global and non-local variable to track that. But it's basically the solution. So let's assume you have some non-local variable here. So note, this is the inner function. This is the inner function. So I'm going to create a variable here called results. That is going to be false. You know, you're telling yourself you cannot do it. You cannot solve it. Then you call your solve, starting from the first element. So I0, then your stack is going to be the empty list, right? So here I'm going to have, no, and these parts will go over next week again. So just, then you just do like solve.
Oh, okay. I've done like
Oh, sorry, give me a second. Okay, just have non-local results like this. Then if it's possible, just set result to be equal to true, right? And you return. And that is the whole solution to solve this question. That is the whole solution. That is the whole solution. So here, if
Okay, so
at the end result is
so
true,
if,
result is true, just do it.
okay, so if the question asks you to return like all possible combinations, that
All possible
cannot
combinations. So that one is
like,
simple, right? The only thing you do is, instead of result is equal to true here, you just append. If it's equal to stack, results dot append your stack,
okay.
empty your stack into it, right? And don't return, don't hit return, because you want to continue and check the other ones, right? There's a slight thing
So
about
if,
relation here, but that's it. Yeah.
so if after appending to the results, after appending the stack to the results, are you supposed to empty the stack since adding any other number is going to exceed that target?
Good. So you can see what I did here. Can you see this thing I did here? I made a copy of it, of the stack. So I create a new copy and I append it to the result.
Oh, okay.
Because list are reference types, yeah.
Oh, okay.
Yeah. So this, I just want to have this template. Well, next week we go into it a bit more. Does that make sense? So this is basically, now I want you to see, this thing looks like magic. When I learned this tree, this thing, it looks like magic. I want you to spend some time and look at it. Try to build it yourself. And you realize this code, this simple code, this 4 lines of code we wrote here is simply doing this. And all you need to do is just to do this condition here and you're done. Yeah.
So is this how do you call it? This algorithm, so to speak, is it in the same ballpark as 0-1 knapsack?
What did you say? Yeah, exactly. It's the same as the 0-1 knapsack problem. The same thing.
Okay. All right.
Yeah, it's basically the same as the 0-1 knapsack. Yeah, go for it. Yeah, there's Billy and there's Eden. Yeah, what's the question? Yeah.
Yeah, correct me if I'm wrong, but is the time complexity going to be
Oh, good question. What time? Who knows the time complexity? Now, in the worst case, what do you do? So let's assume, in the worst case, what you're going to do, let's assume the answer is 5 here, right? You're going to end up building like the whole tree and everything, right? The time complexity is actually proportional to this. That is O of 2 to the power n. That is exponential. Yes, that's the time complexity of backtracking. You can make it better by doing something called memoization, which I'll show you later. What do I mean by memoization? You realize that you can see 2 here, right? You can see 2 here, right? You can see 3 here. You can see some 3 here, right? That means that, well, you don't really need to go down this branch, right? Like, you don't need to go down. You will do memoization and some of those things later, right? That's something you can actually prune the tree so you don't go to some, some, what do you call it, some levels, right? There's also another thing we can do with repetition. With repetition, right, we could actually, this part, you can still do I again. When you can still include it again, right? And so on and so forth. Yeah, Eden, go for it.
Wait, okay.
Yeah, my question was, how is it that adding a copy of the stack to the result solve the problem of we wanting the stack to go back to being an empty list?
Okay, so adding the copy does not necessarily make it an empty list. So this is what happens. So let's assume, right, that you come in and the stack here, you append 2 to the stack, right? Let's assume you append 2 to the stack. Then you make the next recursive call. Then it comes again, then it appends 3 to the stack. Let's assume your target is 5, right? So now the stack contains 2 and 3. Are you following? It contains 2 and 3. Then you make the call again, and then it comes here to this place, right? Then you want to use the 2 and 3, right? Does that make sense? You want to do the 2 and 3. So here, what you do is that you create a copy of the 2 and 3 and put it inside. The reason why you should do that is this. If you put the actual stack inside the 2 and 3, that same stack is what is going to be used for the successive recursive calls. So when it comes back here and you pop from here 3, so this is what I mean. So this your result is something like this. You think you put 2 and 3 here like this, but note that lists are reference types. Is that same stack you're putting something here? So in some future recursive call, if that stack.pop is going to, and this is your stack, it's also 2 and 3. When it hits the stack.pop line and removes this 3, it will also come and remove it from here too, because lists are reference types, right? That is something we saw like last month. Does that make sense? So so to prevent this thing from happening, whenever you're accumulating a list, you have to make a deep copy of it, right? A shallow copy is fine, right? Now you realize that you're going to be popping and popping and popping and popping. Eventually, it will end up being the empty list. Another way to think about it is this. When you come here, you exclude. You always exclude. You always exclude. The stack will always be an empty list. So that's why we get this empty list 1. Does that make sense?
Yeah, it does.
Yeah. One way to also help is this. If you do let me show you something. Okay, let me show you something. I want to show you CS 1110 tutor. Let's look at this very briefly. We almost done. I know some of you are tired. The thing was can do. Then we had a list of numbers, then we had the targets. I just want to do a very brief one. Then I have an inner function def solve. Then we have an index I, then we have some stack, right? And then we are like, if I is out of bounds, right? If I is out of bounds, then you can just return false. That means you cannot do it. Now we're going to store our results in some variable. I don't even want to, don't focus on like this non-local and like this other part. I just want to see how the stack gets created. I just want to see how the stack is created, what everything is. Yeah, and then you just do the next thing here, right? If sum of the elements in your stack is equal to your targets, then what you do is you set the results to be true, or you can do it. Then now let's do our include, right? We do our include. So to include, what it is that you add the item to a stack. See, another way to even do it is this. If you don't write good code, you can just do this. Solve of I plus 1, because there's no repetition, then you can do a stack plus nums of I. But this they are not really doing a stack thing here, right? Like this is not really a stack thing, right? Because they're just, adding things together. But I prefer to use a stack. So a stack has two operations: to append and to pop. To append and to pop, and then to exclude, you pop from the stack. So basically, you're undoing what you did here, right? That's what exclude is doing. You're just undoing what you did here. You pop to remove the most recent element. Then you call your solve again. That's your recursive call. And then you have to do I+1. And then you pass the stack in. That means skip this element and go to the next one. So now let's just call our solve starting from the first element. And then our stack is just the empty list, right? But let's initialize our results. That is set to false. Then after this, after our helper function is done executing, results will have the right value here. And if you want to be even a bit tricky, we can actually do is this. If results has been set to true, all right, you can just do return, right? Like if result has been set to true, you can just do the return. But don't think about this. I just want to see how the call frames are just created. Now look at this. Okay, let's visualize this code. Syntax error. What's that syntax error here? Oh, you just need one of this. Okay, now look here. I just want to see how the things are populated. This is what I did to really get a good grasp of this. Now look at this. We didn't call the function. Let's call the function. Yeah. Yeah, sure. Yeah. Okay, let's add a number 4. And let's put, let's say 5 here. Okay, now let's see the magic work. We hit this. Look at what is going to happen. Is everybody following? Please follow this one. Can everybody see my screen?
Yeah.
Yeah.
Okay, please follow this. This is why I did to get good grasp. Like I visualize it. So look at something here. Forward. Now look, we have let's start this. So we have so this is our first function called function 1, right? Can do. And we have, let's solve this. So we call solve. This is the first call to solve. Our first call to solve, I is on 0. Yeah, that means we're on the first one, right? We're going to process the first one. And our stack, as you can see here, is the empty list. As you can see here, ID 4. You can see it here. Then I go to I check if I is equal to length of numbers. I has not come to the end. I is just on this first number, right? I is not even at the end. So I continue. Then I check the sum of the stack. The stack is the empty list, so the sum is 0, right? So I don't do anything. Then I'm going to include. So look how the include is going to work. The include includes, appends nums of 0, that is 1. So this is my stack. So now it contains 1. Then I'll call the function again, I'll make another recursive call. Then I call this again. Look at what is going to happen again. Then I come include again. These conditions don't hold. Then now I do stack.append. Now I is 1, right? In the next recursive call, because you increased I by 1 here. So now you see your stack. You see the same stack that is being used. It's the same stack, right? So then you've included nums of 1, which is 2. So now you have the 2 here. Then you call include, you're going to the next element. Then here you come again. Now I is 2. That means you're going to 3, right? You're going to now I is standing here on 3. So then you include, and then, so now your stack contains 1, 2, 3. Then you go on again, and then, 3 goes to the next one, include 4. Then you come again, and now we've gone to this case. I has got to the end of the list, right? I is 4. So you see that we have generated one subset. What subset is this? This is a subset containing all the elements, containing the set itself. Can we all see it here? And we have got to the end. Can we see it here? So here, at the end, we are returning. Does this make sense? How? So now we have gone down one branch. We have gone down the branch. We have gone down that branch, that tree. Let me show you something. Zero one knapsack. I just want the picture to show you. Okay, so this branch we just did is this one, right? Wait, I want to show you. So this branch we just took was this. We did include. So we have gone down now and come to like the original thing, right? This is actually with repetition. Let me. I wanted to show you the. These people don't even write clean stuff. Okay, so this is wait, sorry, I want to show you a very neat one. So I want to. So I'll make this thing bigger. Okay, So this thing you can see here, so this is our stack, the subset thing here. So include, we included 1, right? That's the first. So the pointer is like your I. Then if you do include again, we include, then we include. So what the branch we just traversed is the one where it is always include. We did include, then include, right? We did like include, and so on and so forth, right? Yeah, they stopped when they found the target sum, right? So that's what we're doing here. Then look at the cool part here when we backtrack. So now we have got to this part. So we are returning because we've hit, bottom. Then we return. Now you know that, so we return false here. Look, this call frame was triggered by the include of this call frame, right? So we hit false like this. So we are done with this call function call. Then we come to the pop here. What is the stack? 1, 2, 3, 4. But I want to go to the branch where I exclude 4. So stack.pop gives me this, right? So now I call the function again. And then it gets to the rock bottom. Here's rock bottom. So this is also the subset that contains only the elements 1, 2, 3. Does that make sense? Does that make sense?
Yeah.
Yeah. That makes sense, right? So this is a subset that contains elements 1, 2, 3. That is that branch, right? That contains just 1, 2, 3, like just 3 of the elements. Okay. Then we return again. Then, okay, so that was also triggered by this function call, right? Then we come here. And then, so now we are back to this guy, right? And then that is also, so the stack is 1, 2, 3. So now we pop. Now it has 1, 2. Then we continue, that also, so now we're skipping 3. So now we're going to get to the branch that is 1, 2, 4. And now that is 1, 2, 4. So now we've got a subset that is 1, 2, 4. We're going to return now because we've got to the end. You can see we're basically generating the subsets. Does that make sense? That is the cool thing about it. So I want you to spend time to go through this backtracking thing. Please spend time. It's not hard. Like try to visualize the thing. Try to make it make sense to you. And when you're done, so this way we're doing intervals and backtracking. It makes so much sense. Next, we will do memorization and all those cool stuff. But I want you to go here, go to backtracking, and do these ones. See, they're the same thing. Like if I show you, see, it's literally the same thing. Like the approach is like the same thing. See, these things are not scary. Trust me. Look, this is a subset sum problem. This is my solution. See, even when I used to write this, I used to add comments to it. Include a spell. Look at this solution here. I can't answer this call right now. Just text me. Then, so this is a solution for subsets. Now let's look at the other one, combination sum. You realize it's a similar thing, right? It's like, that's why I'm saying this. As you're practicing now, learn the solution, like learn the problem, learn the solution. But there's so many questions you're come across that would just use the same thing. It's the same thing here, right? Include, exclude. This is the include, right? And this is the exclude. Here, the include is like, here they're subtracting from it, right? So if the total is 0, what we were doing was we were trying to build up. We're trying to build up, right? Like we're trying to build up. And you can also build down. Where include means, if you include the number, that means you subtract it from the total, right? Does that make sense to everyone? Like including the number means subtracting from the total. If you don't make, let me show you. I think I have another solution where so this is where I'm also building from top to bottom, right? But there are like so many ways to, but it's the same thing. So yeah, so this may make sense to people, right? This is the same one we wrote. So yeah, include means you append it, right? Exclude means you pop, right? So I can just move this one down here, right? Just like this. Yeah, basically that. And so you see, it's the same thing, Permutations, the next thing we will consider. Permutations, I'll show you. Permutations, it's also similar. Like find all permutations of a string. A very good thing to know. Then I'm going to assume the function works. Find a permutation of all the numbers and just insert these into the different positions. It's a very simple algorithm, I'll show you. And then subset 2, combination sum 2, they're the same things. Okay, I've taken a lot of your time today, but I just wanted to know these things are not scary, to be honest. They are so not scary. Sorry, my back is hurting. Once you invest a good amount of time to them, they are very manageable, super duper manageable. So this week we do intervals and backtracking. I can put resources together for you if you want to go through some resources, but definitely solve the problems. And yeah, just spend this week, munching these 2 topics and you'll be set, to be honest. After this, to be honest, we can even stop the technical sessions after we do a, what do you call it? Maybe base manipulation and a few things and a few graph algorithms and you are set. All you have to do is just practice a lot because we've covered almost everything you need, to be honest. My first recruiting, I did in 2022. These are kind of the things I had just covered and just a few more. And by goodness, I was very fine. Just learn them well, right? As I said, as you're practicing now, learn them. Because if you've realized we just learn one thing and we just extend it to so many things, right? So many things. I'm like, now, spend time, take your time and learn the stuff well. Okay, this is it. And yeah, we're done today. Oh, upload the videos. Yes, please, I will upload the videos. I didn't even upload last week's one, right? Sometimes I get so swamped and I have to also do other work stuff.
Yeah.
But I will upload them. I will upload them. If I don't, someone should just ping me, DM me. Just be like, videos. Okay. All right, I have to go now. I will catch you guys later. Okay, bye.
The
Bye.
the reply don't come out.
The reply don't come. See, now what I do, wait, let me